friends, today I will discuss the numerical problems on network theorems. So let me consider first Thevenin's theorem. So Thevenin's theorem is used to get a practical voltage source with respect to the terminals under consideration. Here, this is the circuit: 60 volts, 10 ohms, 6 ohms, 4 ohms, and we require the Thevenin's equivalent circuit with respect to AB terminals. So to get the equivalent circuit for this, the first step is open the terminals A and B like this. The next step is find out what is the voltage across the terminals A and B. That is 6 ohms is connected between A and B. This is A terminal, this is B terminal. And this is a simple series circuit. So if you find the voltage across the 6 ohms, that will become the open circuit voltage across A and B, and that is called the Thevenin's voltage, and we also call that as VAB. That is equal to 60 into 6 divided by 10 plus 6. So 60 divided by 10 plus 6 will give the current flowing in this circuit. Multiplied with the 6 will give the voltage across 6 ohms. So after simplification, we get here 22.5 volts, and this voltage is called the open circuit voltage across the terminals A and B, which is called the Thevenin's voltage. Next, we have to calculate Thevenin's equivalent resistance for the given circuit. For that purpose, so open circuit the terminals A and B just like this, and short circuit the voltage source which was here, that is 60 volts. Then if there are any current sources, open circuit them. Because here it is only voltage source available, we short that voltage source. So then we get 10 ohms in parallel with 6. So the resultant of 10 and 6 is nothing but the Thevenin's equivalent resistance. So that we can write as 1 by RAB, which is also equal to 1 by R Thevenin, is equal to 1 by 10 plus 1 by 6. After simplification, we get R Thevenin, which is also equal to RAB, is nothing but 3.75 ohms. Once we know the Thevenin's resistance and Thevenin's voltage, we can draw the equivalent Thevenin's circuit for this given circuit with respect to terminals A and B like this. 22.5 volts is the Thevenin's voltage, 3.75 ohms is the Thevenin's resistance. This is the equivalent circuit of Thevenin's theorem. Suppose we want to know the current flowing in the AB terminal resistance, that is 4 ohms, then connect that 4 ohms between the terminals A and B, then find out what is the current flowing here. That is, we get I is equal to 22.5 divided by 3.75 plus 4, that is equal to 2.9032 amperes. So in the Thevenin's based problem, there are only two parameters to be calculated. One is Thevenin's voltage, the other is Thevenin's resistance with respect to the terminals A and B with AB terminals open. So when the load is connected between A and B terminals, so the current also can be found using the Thevenin's equivalent circuit like this. Let us take another problem. So let me take another problem based on Norton's theorem. Norton's theorem is nothing but it is a theorem which is used to get a equivalent to practical current source with respect to the terminals A and B. Here the terminals A and B are under consideration. So for this, to get the Nortons equivalent circuit, the first step is the current calculation, that is called the Norton's current calculation with respect to the terminals A and B. To get that Norton's current, short circuit the terminals A and B like this. Short circuit wire means it is a zero resistance wire and it is in parallel with the 4 ohms. So the resultant of that will be 0 ohms, means again it will become a short circuit. So the circuit will become like this. Now 6 ohms is going to become in parallel with 0 resistance. Then the resultant resistance of 6 and 0 is again 0 ohms like this. And then the circuit we can draw like this. So this 6 and this 2 are replaced with the short circuit like this. Now find out what is the current flowing between terminals A and B. Means find out what is the current flowing here. That is 60 divided by 10. So we get here 6 amperes. This current in the branch AB is called the Norton's current or short circuit current. This is also called the current between the terminals A and B. This is the one parameter to be calculated, so which is calculated. Now, the next step is finding the Norton's equivalent resistance with respect to the terminals under consideration, that is A and B. And this Norton's equivalent resistance calculation is equal to the Thevenins equivalent resistance calculation. There is no difference at all. So when we open the terminals A and B, then so for this circuit we open these AB terminals, means 4 ohms resistance should be removed. Then short circuit this voltage source. So then we get the equivalent circuit like this, 10 ohms in parallel with 6 ohms. Then find out what is the equivalent resistance between terminals A and B, that is 1 by RAB is nothing but 1 by R Thevenin is equal to 1 by 10 plus 1 by 6. So after simplification, we get R Norton, which is also equal to RAB, is equal to 3.75 ohms. So then, so having known the Norton's current and also the Norton's resistance, we can draw the circuit like this. Current source in parallel with the resistance. This resistance is called the Norton's equivalent resistance. This is also called Thevenin's equivalent resistance, whereas IN is the Norton's equivalent current. This is also called short circuit current, which is already calculated. That value is 6 amperes. Similarly, our Thevenin calculated, which is also equal to the Norton's equivalent resistance, that is 3.75 ohms. So once we replace with the values, then this is called the Norton's equivalent circuit. If we want to know the current flowing in the 4 ohms resistor using the Norton's equivalent circuit, we can calculate like this. Connect that 4 ohm resistor between the terminals A and B, then find out what is the current flowing in this. That is equal to, apply the current divider rule. I is equal to total current 6 amperes into opposite arm, that is 3.75 divided by 3.75 plus 4. So that is opposite arms total resistance. Once we simplify this, we get 2.903 amperes. So if we observe here, Thevenin's equivalent circuit and the Norton's equivalent circuit, and the current flowing through the 4 ohm resistor, it will be same, that is 2.9032 amperes. So method may be different, but the solution will be same. or for the current flowing in the 4 ohm resistor. Let me consider a problem based on reciprocity theorem. The reciprocity theorem says that with respect to the any branch, the ratio of the excitation to the response is same when they are interchanged. So here AB terminals are given with respect to which reciprocity theorem should be applied. To apply the reciprocity theorem, the condition is only one source must be there in the circuit. So for this circuit, 60 volts is the source. So there are no other sources. So a reciprocity theorem can be applied to this. Excitation means here it is voltage, that is 60 volts. A response means the current that flows in the AB terminals, that is 4 ohms. Then, so let us calculate the current flowing in the 4 ohm resistor using the ordinary rules. First calculate what is the total current supplied by the 60 volts. That is nothing but 60 divided by 4 in parallel with 6, and that combination is in series with the 10. So once we simplify 4 in parallel with 6, then we get 2.4 plus 10. Then once we simplify this, that is equal to 60 divided by 2.4 plus 10. We get 4.838 amperes. This is the total current. But the current flowing in the AB terminals, we call that as I1. Apply the current divider rule to get the I1. To get this I1, multiply this input current, that is total current supplied by the source, with the opposite arm of the 4 ohms. Opposite arm of the 4 ohms is 6 ohms. That is equal to I1 is equal to IT1, that is supply current, into opposite arm to 4 ohm resistor is 6 divided by sum of the parallel resistors, that is 6 plus 4. So once we substitute the IT1 here, that is 4.838 into 6 divided by 10, we get 2.903 amperes. Now, excitation to the response means that is applied voltage, the branch current which is under consideration, that is AB terminals. Here it is the current is I1. So V by I1 is nothing but 60 divided by 2.903. Then we get here 20.68 ohms. So in the second stage, move the voltage source to the branch under consideration, that is to the AB branch, and short circuit the voltage source here. Then we get the circuit like this. Now the current flowing in the 10 ohm resistor, that is the source original branch current, is I2, and the total current supplied by the source which is in the AB branch, we call it as IT2. So let us calculate IT2, then we calculate I2 using the current divider rule. IT2 is nothing but 60 divided by 10 in parallel with 6 plus 4. Then we get 60 divided by 3.75 plus 4. Once we simplify that, we get 7.741 amperes. This is the total current that comes from this. Then find out what is I2. I2 is nothing but IT2 into opposite arm, that is equal to 6. Opposite to 10 means it is 6, that is 6 divided by 6 plus 10. Simplify that, that is IT2 is replaced with 7.741 amperes into 6 divided by 16, we get 2.902 amperes. Now, this source, original source branch current we call as response, whereas the excitation in the AB branch we call as 60 volts. So V divided by I2, that is 60 divided by 2.902, we get 20.68 ohms. So if we look at this value and earlier value, both are one and the same. So this shows the reciprocity theorem is verified for the given circuit with respect to the terminals A and B. So let me consider a problem. So let me take another problem based on the compensation theorem. The compensation theorem is used only when there is a variation of resistance in the circuit. So look at this. This is 60 volts, 10 ohms, and there is a resistor which will vary from 6 to 8 ohms. Means initial value is 6, the final value is 8 ohms. So to verify the compensation theorem with respect to the AB terminals that is given here, first take the initial value of the resistance, then calculate what is the current flowing in the circuit, that is between terminals and A and B. Then draw a circuit with the final resistance, that is 8 ohms, then find out what is the current flowing. Then third step, find what is the current difference between these above two circuits, that is when 6 ohms is present in the circuits, when 8 ohms is there in the circuit. And after that we calculate the compensation voltage. So let us do first. The first step is take the 6 ohm resistor like this, then find out what is the current, that we call as I1. I1 is nothing but 60 divided by 10 plus 6, that is equal to 16. So that is, we get the current as 3.75 amperes. The step 2 is use the final resistance value, that is 8 ohms between the terminals A and B. Now find out what is the current flowing, that is I2. That is nothing but 60 divided by 10 plus 8. So then we get 3.333 amperes. Then find out what is the difference between the currents I1 and I2. So we call that as delta I, that we get as I1 minus I2, that is 3.75 minus 3.33, then we get difference as 0.42 amperes. Then we can also find out what is the change in the resistance, that is delta R, that is 8 minus 2 is 2 ohms. Then the compensation voltage we calculate like this. Vc is equal to the initial current, that is when the resistance is only 6 ohms, that is I1, into the change in the resistance, that is delta R, that is 2 ohms. So that is 3.75 into 2. Then we get here 7.5 volts as the compensation voltage. Now you can also calculate what is the new resistance, that is R plus delta R, that is nothing but 6 plus 2, that is 8 ohms. This is nothing but final resistance in the circuit. So once we know the compensation voltage and the new resistance, then we can draw a equivalent compensation circuit by short circuiting the original voltage source like this. So by and introducing the compensation voltage like this. Compensation voltage calculated as 7.5 volts, and the new resistance, that is R plus delta R, calculated as 8 ohms, and 10 ohms is already there in the circuit. So then whatever current that flows in the circuit is called the change in the current. So that is delta I is equal to 7.5 volts divided by total resistance, that is 10 plus 8, that is equal to, we get 0.416 amperes. So directly we are able to find what is the change in the current in this circuit by using compensation voltage in this circuit. we can also see the same current in the calculation, that is delta I, that is I1 difference I2 is 0.42. So here also it is approximately 0.42. So this shows compensation theorem is verified for this given circuit. So let us take another problem on maximum power transfer theorem. So the maximum power transfer theorem says the load will receive the maximum power when the source resistance is equal to the load resistance. So this is the given circuit. So for getting the maximum power in the resistor R, which is connected between A, B terminals, so we have to calculate first the Thevenin's resistance with respect to the terminals A and B. For that purpose, short circuit the voltage sources, open circuit the current sources. In this case, it is voltage source, so short circuit the voltage source, open circuit the terminals A and B, that is remove the R. Then find out what is the Thevenin's resistance, that is equal to 10 in parallel with 6, that is equal to 3.75 ohms. That means the load resistance R between terminals A and B must be equal to the 3.75 ohms to get the maximum power at the load terminals. So then, now find out what is the open circuit voltage between terminals A and B, that is 6 ohms, which is equal to, which is also equal to the R Thevenin, that is equal to the open circuit voltage here we call as V Thevenin, which is also equal to VAB. So this can be calculated just by knowing the total current and multiply that with 6 ohms. That is equal to 60 divided by 10 plus 6 will give the current, and multiplying with the 6 will give the Thevenin's voltage across terminals A and B. So having known the Thevenin's resistance and the Thevenin's voltage, we can draw the Thevenin's equivalent circuit like this: 84.35 volts, and the Thevenin's resistance, which we call here as source resistance, as 3.75 ohms. So if you connect the resistance capital R, which is equal to 3.75 ohms between the terminals and A and B to get the maximum power, then we can calculate what is the current flowing in the circuit, that is I is equal to 84.35 divided by 3.75 plus 3.75. So then we can calculate what is the maximum power in the resistor R, that is equal to I square into R. R value is known as 3.75. I also calculated here. The formula is 84.35 divided by 3.75 into 2 means 7.5 ohms. So then whole square, that is equal to I square into resistance 3.75. Then once we simplify the current, that is equal to 11.24 amperes whole square into 3.75. Then once we simplify it, we get 473.766 watts. It's superposition theorem. So this theorem is used to calculate the current flowing in a branch when several sources are present in the circuit. So in this problem, so we need to apply the verify the superposition theorem with respect to terminals A and B like this. So to apply the superposition theorem, the first step is take one source at a time and make the other sources ineffective. In this circuit, two sources are there, both are voltage sources. So in the first step, take the V1 present whereas V2 is absent. That is, make V2 is equal to 0, V1 is present, V1 is active. Then we get V1 is equal to 50 volts. Then the circuit will be as it is. but we short circuit V2 like this. Then let us say the current flowing in the branch AB, that is in 4 ohms, we call as I1. So to get this I1, find out what is the IT1 using the normal rules. That is equal to, so IT1 is nothing but 50 divided by 4 in parallel with 2 plus 10. That is equal to like this. 50 divided by 4 in parallel with 2 plus 10. Once we simplify this, we get 50 divided by 1.33 plus 10 is equal to 4.41 amperes. Then find out what is the I1. So I1 is nothing but IT1, that is apply the current divider rule here. IT1 into opposite arm, that is 2 ohms, divided by 4 plus 2. Then we get 1.47 amperes. Then in the next step, make the V1 ineffective and keep the V2 present in the circuit. So once we make the V1 0, that is we short circuit like this, then V2 will be like this. These are the AB terminals. To calculate the current flowing here, first calculate what is the total current. That is total current is given by IT2, that is equal to 30 divided by 10 in parallel with 4, that is in series with 2, that is 4 in parallel with 10 plus 2. So once we simplify that, we get 30 divided by 2.85 plus 2. So after simplification further, we get 6.18 amperes. Now we can calculate what is I2. I2 is nothing but IT2 into opposite arm, that is 10 amperes, 10 ohms, divided by parallel resistors, that is 10 plus 4. Then simplify this. In place of IT2, use 6.18 amperes, then into 10 divided by 4. So that is equal to, we get 4.418 amperes. So when V1 is acting, the current flowing in the AB branches from top to bottom. Similarly, when V2 is acting, current flows in the AB branch from top to bottom. That is I1 and I2 both will flow in the same direction. So add those two. That is equal to 1.47 plus 4.418. Then we get 5.88 amperes in the AB branch with the superposition theorem. The same value also we can get using the loop method also, because it is asked here to verify the superposition theorem with respect to AB terminals. So we have to calculate current flowing here due to individual voltage sources. Next, Millimans theorem. This theorem is used when there are number of voltage sources, or when number of practical voltage sources are connected in parallel, we get the equivalent practical voltage source with this Millimans theorem. So let us take a problem here. This is one voltage source, that is 50 volts in series with 10 ohms, and 20 volts is in series with the 2 ohms, and 30 volts is in series with 6 ohms. This 10 ohms, 2 ohms, 6 ohms, they are nothing but the internal resistance of these voltage sources. And these voltage sources are connected in parallel. All resistors connected together like this. Here all voltage sources are connected together like this. And this is the AB terminal, and the load connected is 4 ohms. So here first of all we have to calculate what is the Millimans equivalent circuit for this circuit. So to get the equivalent Millimans circuit, first calculate what is the R Thevenin with respect to the terminals A and B. That is equal short circuit all the voltage sources. If there are any current sources, open circuit them. Then remove this 4 ohm resistor also. Then circuit will become like this. 10, 2, 6, all three resistors are in parallel. Find out what is the resultant resistance with respect to terminals A and B, that is equal to 1 by RAB is equal to 1 by 10 plus 1 by 2 plus 1 by 6. That is equal to, we get RAB is equal to 1.305 ohms. Then VAB is equal to, it's nothing but 50 divided by 10 plus 20 divided by 2 plus 30 divided by 6. Get the Millimans voltage. It say that is VAB, that is nothing but 50 divided by 10 plus 20 by 2 plus 30 by 6 divided by 1 by 10 plus 1 by 2 plus 1 by 6. Once we simplify that, we get 20 divided by 0.766. After simplification, we get 26.109 volts. So having known the Thevenins resistance and the Millimans voltage, then we can draw the circuit like this, which is called the Millimans equivalent circuit, that is 26.109 volts in series with 1.305 ohms. If you want to know the current flowing in the load resistor connected between AB terminals, draw the circuit like this, connect that 6 ohm resistor between terminals and AB and find out what is the current flowing in this circuit. So then we get 26.109 divided by 1.305 plus 6, then we get 3.57 amperes.